Yeah, thanks for the organizers for this really nice conference. It's an honor for me to be here and to be able to share my work with you all. And these are the relevant references here. And I wanted to start by acknowledging my collaborators, Anders Sandwick, with whom I worked on this deconfined criticality in a spin model, computing the entanglement entropy. And for this interacting fermionic model, Roman Oruz and Fernando Dewan in San Sebastian, Spain, and Nicolas in Toulouse. And so yeah, my outline is I want to talk about entanglement entropy computations in quantum Monte Carlo simulations, the old and the new variants. And then I'm going to talk about entanglement entropy in this JQ spin model, which effectively realizes a deconfined quantum critical point. And then I'm going to talk about an extension of this technique to interacting fermion systems and the fermionic Hubbard model on the honeycomb lattice, which realizes this Gross-Neveu Yukawa critical point. And if I have extra time at the end, I have something about quantum Monte Carlo and Yang-Lee zeros, but that's if I have extra time. So in quantum Monte Carlo, we sample the partition function. And that can be represented as a discrete path integral here, rolled up on a cylinder. And I'm going to be using this, for spin systems, this algorithm invented by Anders, the stochastic series expansion. So the question is, how do you compute Renyi entanglement entropies in this framework? So you define the reduced density matrix associated with some region A. And then to compute the second Renyi entropy, you just take this reduced density matrix, square it, take the trace, then take the log. And you can actually write this in terms of a ratio of two partition functions which are on replicated manifolds. So ZA and Z0. And these are just defined by sort of continuing with these pictures. This ZA would be this type of partition function where in the region A, there's just a single trace of these spins. And in the complement of A, there's two traces. And then Z0 is defined in the same way, where there's no sites that are traced once and all the sites are traced twice. So this is actually just the partition function squared. So there's been lots of work from the quantum Monte Carlo field to be able to compute these partition function ratios. And it started with things like a swap operator computation, and then also thermodynamic integration of the energy differences between these configurations is another way to get that. And then another popular technique was to use Monte Carlo to sample the union of these two ensembles, this ZA and Z0, and you sort of do a random walk in that space of those two types of configurations, and then you just count the amount of time you spend in one ensemble versus the other, and then you divide that, and that gives you an estimator for the partition function ratio. And these techniques actually worked very well, and there's lots of information that can be gathered from the simulations. But there's another very powerful framework that can be used in this types to evaluate these types of ratios, and that's what I'm going to show you now. And it's based on classical free energy differences. So if I were to be able to interpret this as a classical system where in the vertical direction these would be real couplings appearing in a classical Hamiltonian, then to go between the two ensembles, I could just turn on these couplings to some finite value and join these two things together. And so I'd be able to go from the Z0 ensemble to the ZA ensemble just by increasing these couplings. And as I increase the couplings, since these appear in the classical Hamiltonian, I know the energy difference as I increase this coupling. And so I know the work that's done on a configuration, an incremental piece of work. And so I can compute in some non-equilibrium fashion the work that's done in order to go from this ensemble to this one. And so you could use Jarzynski's equality, which says you take the exponential of the work, and that gives you exactly this. In this case, it would be the second Renyi entropy. So this is exactly what was done by Vincenzo Alba in the case where this was a classical Ising model. at the critical point and used it to get the second Renyi entropy and showed that it shows perfect agreement with the Calabrese-Carty formula for the central charge. And so the question is it how could you extend this idea to quantum Monte Carlo simulations where now this is not, the vertical direction is not a coupling and a Hamiltonian. This is just imaginary time evolution, and these things just differ in their trace condition. So how can we extend this? So the idea is to introduce a field that will couple to the trace. So you could do it in the following way, where for each site in the A region, you could introduce some weight factor of 1 minus lambda times that site being traced twice, and then add to that a factor of lambda times that site being traced just once. And then you just tune lambda going from 0 to 1 in such a way that you go from the Z0 ensemble to the ZA ensemble. And of course, everything outside of the A region is just always traced twice. Now, what does that actually correspond to? It's, if you do this for every individual site in the A region, and then you expand that out, it becomes a weighted sum over partition functions, or these replicated partition functions where this thing is now, it looks like the ZA ensemble, but now it's over this subset entangling region C. And now this weight factor outside, which depends on lambda, it just cares about the number of sites that are in this fluctuating region C. So it's like a grand canonical ensemble, but it's not the particle number that's fluctuating, it's the entangling region itself is allowed to fluctuate. And this ensemble can be simulated perfectly well with quantum Monte Carlo techniques. And now once we have this thing written down, we can identify what would be the corresponding work increment if you were to take this lambda coupling and increment it or change it by a small amount between 0 and 1. So now we have our work. And then again, this thing, it only cares about the number of sites that are in this fluctuating entangling region. So now I have a movie that kind of represents how this goes for this would be for the Heisenberg model on the square lattice. And now black means it's traced twice, and then orange means it's traced once. And so you start out, everything's traced twice. Then as you're incrementing lambda, now things are becoming more and more just single trace sites. And I kind of like to think of this as almost like it's like a dimmer switch. You know, you're sort of like very slowly going between these two ensembles. And so if you actually use this to compute the second Renyi entropy for the Heisenberg model, then this is where you could take a rectangular system, L over 2 by L, and then you're now able to compute the second Renyi entropy on system sizes that are an order of magnitude larger than were previously possible with the old techniques. And in this case, since it's a Heisenberg antiferromagnet on the square lattice, it's magnetically ordered. There's Goldstone modes associated with the Néel order. And so this is formula by Midlitsky and Grover, which says that the Goldstone modes will contribute a log to the entanglement entropy scaling as a function of system size. And the coefficient of the log tells you the number of Goldstone modes. So one kind of take home from this is that actually for the Heisenberg model, even when you go to massive system sizes, there's not great agreement with this formula. So one needs to consider finite size corrections to this scaling form. So now I want to talk about entanglement entropy computations in the JQ model, which effectively realizes this deconfined critical point. And so I want to start by kind of summarizing the work that came previously that inspired this work. So it started off with this really nice work, which was the first one to compute entanglement entropy at the deconfined critical point of the spin model. And so what they did was to take some region A, a square which has these sharp corners, and then the prediction is that, well, if the system is described by CFT, then you would expect that these corners would contribute a negative log to the entanglement entropy scaling, and then the coefficient of that log would be a universal number. On the other hand, if it were not described by the CFT, but if there's Goldstone modes present, then the predominant scaling would be now with a positive log, and again, you would have the number of Goldstone modes appearing. So then they did the simulations. They used a variant of the previous approach that I was just showing. And so what did they find? They found that actually it's a positive log that's appearing. So it's sort of, this would be indicative of if there were some magnetic order happening at that point, which might reflect that the fact that it's weakly first order. Now there's evidence to show that it's weakly first order at that point. So beyond this, there's more recent work that used an improved scaling form for this, the Mitlitsky-Grover formula. They use an improved scaling form and showed that actually it seems to be approximately 4 Goldstone modes that can be detected at that point, which is what one would expect if there was a SO5 ordered moment at that transition point. And then beyond that, there was these authors extended this to an SUN model and then showed that the sign of the logarithmic term changes as you increase the number of colors in this SUN model, which would seem to indicate that it'd be weakly first order beyond these when this is less than this number of colors, and then when it's larger, then it's described by a genuine CFT.
So what happens is the smooth boundary will give you a log, and that log will vanish at NC about 7.
Okay, so.
Interpretation of the.
Oh, okay, I see. Yeah. Yeah, okay. Yeah, so to put it better is that if there's magnetic order, you have Goldstone, you can detect the Goldstone modes even when you make a smooth cut. But then if you're at a CFT, a smooth cut should give 0 log with just pure area log. And so that was the criteria that was used to determine this value of NC. Yeah, okay, sorry for misspeaking about that. So thinking about wanting to study this system myself, I was interested in this separate work that was actually on a fermionic model for deconfined criticality. And what was used was on the square lattice, they took an entangling region which is tilted by 45 degrees. And so I thought that, this would be a nice, actually, prescription for or a different way of looking at potentially if you can find agreement with the CFT form. So now this is where my work comes in collaboration with Anders, where together we studied this JQ model, which is just essentially this Heisenberg model supplemented with an extra 4-spin interaction. And all the interactions in this model can be written in terms of a singlet projector. And now the story goes that this model is effectively realizing a deconfined critical point between this Néel-ordered state and then this VBS state as you increase Q. And the point is that even that there's evidence that it's weakly first order, you should be so close. You should still be able to extract meaningful information about the critical point. And so that's what we're aiming to do in this work. And so now I want to talk about kind of like the importance of the different entangling cuts and why maybe the tilted cut could see things that you're not going to see with this regular straight cut. So if you imagine 2 different types of VBS patterns here, and how a cut would be influenced by this. If I make a straight cut on the square lattice, this pattern, these bonds are unhappy. Whereas, this one, they don't even feel this cut, or much less than these do. So it's not treating all the VBS patterns equally. Now, on the other hand, if I take a tilted lattice and then make a cut through there, this is now treating all the VBS patterns in the exact same way, which is kind of what you would want if you want to preserve the physics of the deconfined critical point and not, you don't want to be biasing one component of the VBS field over other ones. So the first thing that we wanted to look at were smooth cuts of the system. And we looked at it for actually 2 different aspect ratios, aspect ratio 1 and 2. And we just compute the half entropy with a smooth cut. You see, on a torus, this doesn't, this is wrapped around the torus, so it doesn't form any corners. And so the point is that at a critical point, then you would expect that there would be 0 log contribution for these smooth cuts. So this is the data that we have for the tilted square lattice is in the red with the 2 different aspect ratios, and then the square lattice is in black. And then here I'm just showing the raw second Renyi entropy data as a function of L. And now on this side, what I'm doing is I'm fitting to an area law plus a log. And then I subtract away the area law piece from the data, and I plot the resulting data on a log scale. So this is just revealing the logarithmic piece, and the slope of these lines is telling you what the coefficient of the log is. So it's looking like this tilted square lattice is really giving essentially 0 logarithmic contribution, as you would expect at a critical point, whereas the square lattice with the straight cut, it's showing these values for the logarithmic piece, which has the sign that's a positive sign, as if we're to come from gold cinemas, and it actually is increasing with the aspect ratio. But if you go to higher aspect ratios, then it's pretty much at this value. It doesn't continue to increase. Now, there's a subtlety actually with this data in that for the tilted square lattice, now the way that the lattice is defined, you can actually perfectly well put it on an even size system or an odd size system. So you could study this straight cut in both cases, and there's actually an even odd oscillation in the data. So then you can look at those 2 series separately from one another, the even series and the odd series, and it seems that the even series does show a small logarithmic piece, which is much smaller than the coefficients we were seeing previously. So this is 0.04 plus or minus 0.01. So this is statistically significant, although I couldn't quite tell the difference between this versus a 1 over L correction either. But this is definitely there. But the interesting thing is, for the odd system sizes, this really does just seem to be completely area law, 0, without any corrections beyond that. Actually, I forced the fit equal to 0 in this one, but statistically, it's the same as 0. You can see it gives a great fit with just the pure area law. So then now we want to move on to what's the corner contribution? Can we get this universal coefficient of this log that you would expect from these corners? So we study the square lattice and the tilted square lattice. And again, if this is described by a CFT, then the corners are going to contribute a negative log with this universal number. So again, I'm now plotting the raw data, S2, where I'm going for the tilted lattices, I'm going up to 72 by 72, which would correspond to essentially the equivalent of 100 by 100 square lattice with these massive entropies as well. And so I do the same analysis that I was previously doing. I do a 3-parameter fit, and I subtract away the area law piece, and I reveal the logarithmic piece. And you can see now that the tilted square lattice has this negative log, which is what you would expect from the CFT prediction, whereas the square lattice, as was previously found, has this positive one. We get a value that agrees with what was previously found. But the interesting thing is that if you compare with what the corner coefficient, yeah.
Where does that CFT prediction come from? The SO5 CFT?
For this one I'm comparing to a free 5-component scalar field.
But why would the free theory have the same answers?
Yeah, so it's actually not, I mean, this is just a rough comparison, and we're going to see later, actually, that I'll explore the angle and show that it's different from this value. So it's not, and actually for the O3 model, it's, from numerics, it's been shown to be less than just three scalar fields. So,
yeah, but I'm saying, like, I can understand Wilson-Fisher theory might be close to free theory, but this SO5 theory is supposed to be completely different from Wilson-Fisher, completely different from free theory. Why would you be remotely?
yeah, well, naively, my thinking was that this ought to be described by some critical SO5 vector. And so then the most rough comparison to make in my mind would be to compare to a 5-component scalar field. It's basically, one can just take away from this that there's a large value from this corner coefficient, which is meant to roughly count the number of degrees of freedom. It scales with the number of degrees of freedom that are at the critical point. So it's just interesting that it comes with this larger value. And it happens to be very close to this n equals 5 value. So it's, yeah, I guess one shouldn't read into it too much. And I'll show something later that's, you know, it's not, one wouldn't think that it would be this exact value. And we'll see that it is actually different for different angles. So this, now you're getting the critical scaling for this tilted lattice. And now we saw previously that there was an even odd effect that had a significant effect on the data. So one would worry that there could be some even odd effect going on here, and then maybe the extracted coefficient could be sensitive to that. So we do the same thing from this tilted lattice, do it on even size systems and odd size systems. And actually for the odd size system, the region is defined slightly differently, where it has this, now this C4 symmetry that the other one didn't quite have. And now if you do compare the even series and the odd series, they really give essentially the exact same corner coefficient. And again, this is the n equals 5, which, yeah, take that with a grain of salt. It's not really, I don't think, it's not meant to agree perfectly with this value. So now, what I alluded to is that we did the case where we have a region with 90-degree corners. So and we use a tilted lattice to be able to set things up in a nice way, to be able to do the scaling. We just take, you know, unit cells tilted by 45 degrees and then take an L over 2 by L over 2 section of that, and then we have a nice square region. But we can look at other angles if we defined the square lattice by using different numbers of unit cells. And then it's kind of just a convenient way of cutting out an L over 2 by L over 2 section of unit cells, and now you get different angles. And one should be careful about, so I'm showing here these unit cells and how I'm building this square lattice, and this is just an L over 2 by L over 2 section in the middle, and now I'm getting this parallelogram with these different angles in it. And one needs to be careful about choosing the cuts in such a way that you're not selecting one VBS pattern over the other ones. These still have the property that all VBS patterns are treated the same way. So now we can look at the scaling of these parallelograms on these lattices with different numbers of unit cells. And so here I'm including the previous data from the case where it's just I used a 2-site unit cell, so it's tilted by 45 degrees. These are 90-degree corners. And in the inset, this is just, I've already done the analysis where I subtract away the area law, and so I'm plotting. Now, this is as a function of the acute angle theta in here. And so, as you see, that as this theta becomes smaller and smaller, the value for the corner coefficient is increasing, like this. And so, this is now I'm comparing with a 5-component scalar and how that behaves as a function of the angle. So you can see that in the case where there's a small angle, there's a very significant deviation away from this 5-component scalar. But the important thing is that it's behaving in the same way as these CFTs behave, in that this corner coefficient is increasing as this small angle gets smaller and smaller. So at this point, now I'm going to switch gears to the extensions of the interacting fermionic models and the Honeycomb-Hubbard model. So I just want to, I'm happy to say that this work finally got accepted. So I feel like I need to brag about that, because if I don't do it, then nobody will brag about it. So this is, now I want to introduce pictures again to kind of represent the configurations, just like before, but now these are meant to represent an interacting fermion, a path integral for interacting fermion model, which has already been, these black and white circles here are not spins, but there's these Hubbard-Stratanovich fields that have been used to break up all the interactions. And now an important quantity in these simulations, which I'm denoting by this green bar, are the Green's functions, the 2-point functions for the fermions, which depend on these Hubbard-Stratanovich fields. And I'm considering 2 separate configurations because I'll be looking at the second Renyi entanglement entropy. And so if one wants to compute this Renyi entropy, what you need to do for a region A, you just take the Green's function and you restrict it to the region of interest, A, make a smaller matrix out of that. And then Tyrone Grover showed the prescription for how to compute the second Renyi entropy. You just take these matrices, you multiply them together in this fashion to get this, what I'm going to refer to as a Grover matrix. And then once you have that, it's a very simple prescription to compute S2, where you just take the average of the determinant of this Grover matrix. And the average needs to be taken over the Hubbard-Stratanovich field configurations for both of these replicas. So this is an extremely elegant way to compute this thing, and there's been lots of work using this and also using different formulations to be able to compute this. The problem is that this suffers from, this observable has a long tail distribution. It suffers from these rare events. Essentially, you're sampling from an uncorrelated ensemble and then trying to infer properties of an ensemble that's vastly different from the one that you're simulating. So in order to get past this problem, one needs to introduce an interpolating ensemble that can go, between, which is the exact thing that I was using before in the spin case. So in order to make this work, you need to write this thing in such a way that it looks like a ratio of partition functions. So I'm just writing the average of this Grover determinant of the Grover matrix, writing it. Now, instead of summing over the probabilities, I'm summing over the quantum Monte Carlo weights for these guys, multiplied by the determinant. And normally, rate how you just divide by the sum of the weights, so you get the probabilities. But now I'm going to insert a factor of just 1, because I can interpret in the denominator as being the determinant of a 0-dimensional Grover matrix. And the determinant of a 0-dimensional matrix is 1. So again, this is just like a ratio of partition functions. And I can now interpolate between them using this, actually the exact same ensemble that I was showing before, where I just let this region fluctuate. Now, although the formulation is exactly the same as I showed before, there's major technical hurdles that need to be overcome to be able to implement this in an efficient and numerically stable way. But in a sort of miraculous way, that can all be achieved, and it sort of just goes through very nicely. And I also want to point out the fact that after this work, there was another work that builds on this, that Yuanda Liao, he introduced a much better interpolating ensemble, actually. So if you're interested in these simulations, I would say you should use this one. But still, we're able to get very nice results using this ensemble here. So let me show you, the first thing we want to do is to look at this honeycomb Hubbard model. And we want to just verify that this code works properly. So I now use this QMC technique, and I compared with these quasi-exact results from DMRG. I used the Julia iTensors package, which was very convenient to do this. And so I just on a 3x3 little honeycomb cluster, and I compute the S2 for this region. And now as a function of U, I get perfect agreement between the DQMC and then the DMRG. And then this zoom in is just for one of these data points. If you just measure more and more and more, then you just hone in on the exact value. And so you can already start to see the kind of features of the phase transition here, where at small u, you have a Dirac semimetal, and then at larger u, you have this Mott insulator. And then there's the Gross-Neveu Yukawa critical point in between. And so we want to investigate this kind of phase diagram by looking at these regions with corners in them. And we saw previously that these things can depend massively on how the regions are defined. So actually we want to study 2 triangular regions of this honeycomb lattice. This was the first one I used, and then later I looked at this one, the zigzag triangle and the bearded triangle. And so again, in a critical state, one expects that there'd be this negative logarithmic contribution, and then in principle this coefficient should be a universal number. And so now let's look at kind of what the data looks like. Again, I'm just always doing the exact same analysis, even as I was doing previously, where now I'm setting u equals to 1 in the semi-metal phase, and I'm studying the scaling of these two types of triangles. This is just the raw data. And then now in the inset, I've done the 3-parameter fit. I subtract away the area law and plot the resulting log. And so all I care about is the slope. And you see that both of these triangles give essentially exactly the value that you would get for free Dirac fermions, which is the description of the semi-metal phase. And now the interesting bit comes when you go now to the critical point. And can you see a difference between these two things? And so it turns out that this zigzag triangle seems to give the exact same value as it was giving at u equals 1. There's no difference. And then, but if you look at this bearded triangle, now it looks much more negative. So there's sort of an enhanced value here. And then what I'm plotting for comparison, again, it's not a great comparison, but it's the most rough sort of comparison you could do, which would be to consider what would you expect from free Dirac fermions plus a three-component scalar field, which is representing this critical nail vector. And so it's roughly in the ballpark, which, it's not to be strictly compared, but it's encouraging and makes you want to study it kind of as a function of u and see how this thing evolves. So now we're focusing on this bearded triangle, and now you can collect all this data as a function of u for these different system sizes. This was actually aided by the fact that we found that these universal log terms are not sensitive to the Trotter slicing. So you can just take a fat Trotter slice of like 0.5 and then collect all this data. And this is the raw data. And now for each value of u, I do this fit and I get the log piece. This is what the log fits look like. And then the extracted corner coefficient as a function of u. And you can see this bump coming at right where the critical point is supposed to be, around 3.8. So this is, to point out, this is the first time, to my knowledge, of being able to detect these logarithmic terms in a two-dimensional model of interacting fermions. And just for completeness, if you go to larger U, where you have a mod insulator, you can, again, compare with this formula due to Mitlitsky and Grover, and you see that you get the expected, essentially, 2 Goldstone modes with a positive log now. So now that wraps things up. And so the take-home messages are that I hope that I showed you that this is a powerful approach to compute entanglement entropy in quantum systems, which is quite general. Can use it in spin and fermion QMC. And for the spin, for the deconfined critical point with the JQ model, it seems that the tilted cut gives all the features that one would expect from this DQCP. But the cut dependence is really crucial. And then as additionally evidenced by the fact that, for instance, in this fermionic point, if you use this kind of the naive triangle, or kind of the first one that you would think of, then you would completely miss this feature at the Gross-Neveu Yukawa point, which is actually originally what happened. And then I studied the deconfined critical point and then went back and studied it with a different triangle and then found this feature. So that wraps things up. And I guess it's right on time. Yeah.
Pass the mic around, but you can go and put the mic. That would be great. Is it on?
Hello? Okay. So for the D2CP, you mentioned the cut dependence probably come from the VBS. You don't want to discriminate some of the VBS pattern, but do you have a similar interpretation for the Gross-Neveu? Because there,
No.
naively,
No.
there's no BBS pattern involved.
Yeah,
right?
no. I really have no idea.
Okay.
Yeah, thank you though. Yeah, it's important to think about though.
Okay, thanks.
In principle, do you expect this dependence on the cut form to go away if, I don't know, the cutted region becomes large or something? Because it seems like it's UV physics.
Right.
Why should it affect the scaling limit? But the plots you've shown, they diverge even more and more as you go to large L.
No. It's not going away. I mean, it seems there's no and we're able to go to massive lattices, and you can just use, only the largest system sizes, and you find that, it's this weird log is appearing, regardless.
But you keep the region that you cut out, its size the same.
Oh no, you scale.
Everything's
being scaled with the system size, so it's always a fixed fraction of. So it'd be like L/2 by L/2 region, and then you just increase L. So yeah, it's somehow profoundly affecting the physics.
So you're computing this partition function as a function of parameter lambda, but it seems like for S2 you just need a derivative, like almost at any point. Is there much more information in this partition function that you can extract? Like
that's
high order entropies or something? Yeah.
That's something that I've been thinking of a lot, for a while. But it's not entirely clear what. I mean, one can start studying things about this generalized partition function, and maybe get some interesting things. But to connect it up with things that are already known, I'm not sure how to do it. I mean, you could of course use it to compute higher Renyi entropies, but that's just a straightforward generalization of it. But to get kind of more detailed information, I'm still not sure. But it's an interesting prospect.
Thank you.
Yeah, very nice talk. So do you have any comments on the same problem when you use this incremental method? For example, if you cut like AB sublattice for this honeycomb model?
A sign problem for the honeycomb model specifically?
The
fermion model?
Yes.
Well, in this case, I was fixing to half filling to, ensure that there's no sign problem. But actually, I forgot to mention that the methods that I was using, it was actually an equilibrium variant of the original, this non-equilibrium process that I was showing. So in that point of view, it's clear how one can still perform the exact same computation, even in the case where you have a sign problem, where it's sort of the standard thing where you have your measurement or the estimator that you're computing, and that needs to be weighted with the sign, and then at the end you divide by the average sign. So you can still compute it even when you have a sign problem, but it's not clear. I haven't looked at it in particular to see how severe the sign problem affects that particular observable, or it's not clear if it's any more mild or just as severe as in other observables. Does that answer the question?
Yeah, we can discuss further. Yeah.
Okay.
You have a few minutes left if you want to. You have some more slides you will show us.
Oh, really? Okay. Well.
Just 2 minutes.
Okay. Okay. Well, since I have some bonus material, then I might as well tell you a separate story. Something I really enjoyed working on. It has to do with these Li-Yang zeros. So actually, this entanglement entropy work, it was all about ratios of partition functions and thinking about free energy differences and things like that. And then, so it got me thinking about, well, just computing free energy differences in standard QMC, where you vary some parameter that's actually inside the Hamiltonian, and then you end up computing the partition function ratio. And then that got me thinking, well, you can identify a formula that allows you to compute that partition function ratio where you've varied some parameter inside your Hamiltonian, and you actually never need to simulate the partition function that appears in the numerator. So then you can take that you're looking at it with a different parameter, you can actually extend that parameter to the complex plane, and you never need to simulate it. And so this ties in with the story of Li-Yang zeros, which it was first studied in the Ising model. And so, for instance, what's the behavior? It's that there's a critical point in the Ising model. There's a singularity in the thermodynamic limit, but finite-sized systems are always regular. There's no singularity going on. But Li and Yang pointed out that if you extend parameters to the complex plane, then there's zeros of the partition function, or places where the free energy is singular. And then in the thermodynamic limit, those singularities approach the real axis. And so they coincide with the real thermodynamic singularity. So this is sort of a cartoon sketch of what it ends up looking like. Is in the Ising model, say you're below TC and then it's ordered. Now in a finite-sized system, you have these partition function zeros in the complex plane. And then as you scale the system size up, these become more and more dense, and then they eventually reach the real axis in the thermodynamic limit. And the way they get there is with a universal power law, which you can use to get critical exponents. And then even if you're above TC, where it's disordered, you still have these zeros, and now they become more and more dense, but they actually end up landing in the thermodynamic limit at a complex value of the coupling. And so this was studied by Fisher and Carty, where it was shown that this is sort of the simplest example of a non-unitary CFT with this negative central charge here. So the idea is, can we extend this to quantum Monte Carlo simulations, like for the first time? And there's been previous work using DMRG, but one would like to really use this large-scale QMC simulations. So I use a test system, which is this Heisenberg bilayer system, which is meant to like a perfect realization of this O3 universality class. And so this is the value of this interlayer coupling that gives you the critical point. And the idea is to kind of build an analog to this Ising case, where now we have an antiferromagnet. So the field that we're going to introduce is a complex Néel field into the problem. So we're going to be simulating, not actually simulating this ensemble, but we're going to imagine adding this complex field coupled to the Néel, this Néel field. We make the H complex, and so there's kind of technical details for how this ends up happening, but I'll maybe just skip to the formula where the magic is that you can do a perfectly normal simulation with no field. It's the most simple setup for the SSE. And then you can compute now this is the partition function ratio between the model with zero field and the model with a field H. But you've never have to simulate this ensemble with the field H. So you can actually make that complex. And so this is kind of what you can check this with exact diagonalization as well, where you just this is a bilayer system with side length 2, so it's 8 sites. And then as a function of this complex Néel field, you can see the behavior of this partition function ratio starts from 1, and then you get these zeros coming. This is where it strikes 0. And now now this is quantum Monte Carlo, so we can go to huge system sizes now with side length 80. And now in the complex plane, you see zeros of the partition function. And so these can be used these will creep towards the real axis in this case, and then the way they get there is with this power law. And so you can fit with it just agrees with the value for the O3 transition. Should I shut up now, or? Okay, yeah. Anyway, so that's essentially the story, is that it can be done in the quantum case. And then there's extra stuff for deconfined criticality if you want to look at the reference. Thank you.
Great, thank you. Thank you so much, John. While under the setting up, you have maybe 50 seconds for questions.
So, what's the magic? I mean, why can't you get around the sign problem?
Because you never have to simulate this. You're comparing two distributions. And so as long as they're relatively close to each other, then that computation is well behaved. So the trade-off is that as the system size becomes bigger and bigger, the window, how far away you can look in the imaginary direction, it becomes smaller and smaller. But the zeros, they also creep down, so you can track the first 5 zeros all the way as they approach the real axis.
So it seems like you can go to very big
you can go to very, well, for small sizes, you can go, pretty sizable imaginary fields, but when it becomes large, for the 80, yeah, I know it was on the other slide where it was like 10 to the minus 3 or something. So, yeah, thank you.
Just a quick question. So it seems like one of the results of your talk is that you said that, like, depending on the precise method you use, sometimes you find the logarithm of 0 or applying it to CFT, whereas maybe some other method would have thought maybe it's not a CFT. So does that mean, could you also kind of redo the analysis of some of those previous papers that were claiming it was not a CFT for n smaller than 7, and maybe with your new analysis you would now find that it is a CFT for n smaller than 7? Is that a possibility?
Yeah, I would expect that you would still see this like critical log for, even for these smaller values of n, where, yeah, it would just be an extension of that, I would think. But the question is, yeah, is that an indication of the physics that's going on, or is it something that it's the Renyi measurement is just disrupting the system too much? So that's, yeah, not what's clear. That's not clear to me. Thank you.
Thanks a lot.
Yeah.